Okay, we're going to start up here the next chapter. I think chapter 14. This is also exam 2 material that we're rolling into now. So in this chapter, we're really going to begin probably the hardest part of the course for most people, and really where a lot of people do struggle in this course is through this chapter and the next chapter. Is really where a lot of conceptual sort of understanding does need to come into play. You do need to be able to understand sort of what is happening in the problem to be able to solve it correctly. Otherwise, there is a lot of places in these chapters where you can do a lot of math and it's like wrong because that's really not what's happening in the problem. So the good news is a lot of the calculations that we'll talk about in this chapter we've already done in previous chapters. You just got to know how to sort of apply it correctly in the correct situation so that you hopefully don't run into any of those roadblocks. So in this chapter, we're going to talk about buffers. We're also going to talk about titrations, and we'll finish up talking about indicators, I think. So a lot in this chapter. This is sort of, you're thinking about the hill of this class, we're getting to the top of all the conceptual stuff that you also learn in these next couple of chapters. So let's first talk about an idea that's known as the common ion effect. And the common ion effect is an idea where, as the name sort of implies, you have a common ion present. The presence of that common ion does cause a weak acid or even a weak base to basically not ionize as much as it normally would without the presence of that particular substance. So for example, if we had our acetic acid, which is everybody's favorite example. So we take some acetic acid, which is a weak acid, and when it does break apart, it will break apart into H plus and some acetate here. And it is a weak acid, so you're not going to get a lot per se, maybe to kind of come off to begin with here in this weak acid. And it will normally dissociate here and set up this equilibrium. Now, if we took this acetic acid and we also threw in there in sort of the same beaker, if you will, something like sodium acetate. And sodium acetate is a salt. And it is a strong electrolyte, so when it goes for a swim, it's going to 100% break apart into its ions. And when it does so, and it's in that same sort of beaker, if you will, or flask, or whatever it may be in, it's going to break apart into a sodium ion that's floating around and an acetate ion that is floating around. So when we do have actually both of these things together in the same solution, there's a couple things you want to think about. When we have the acetic acid, I'll draw a big beaker here. The acetic acid is the one that's going to set up the equilibrium, which means you're going to be able to keep all three of those things basically in solution at the same time. But when we do have the sodium acetate to it, it is not going to stay together. It will break apart, and that will introduce into our sort of equilibrium sodium ions and acetate ions that are basically floating around. Now, we could clearly see that it is the acetate ion here that is the common ion. And essentially, when we add that sodium acetate to it, we are essentially increasing the amount of acetate, right? And our good friend Le Chatelier's principle would say if we increase the amount of the acetate that's in that solution, the equilibrium should shift which way? Should shift to the left, away from the side at which we added it to. The result of that is it's going to force the acetic acid here to basically stay together. So let's think about really what the result of that sort of effect is. It's going to keep the weak acid mainly together a little bit more than it would be if the acetate wasn't there. That means in terms of pH, in terms of the H plus concentration, would we have more H plus or less H plus in the solution because of this? We would have less, right? Because the equilibrium shifts to the left, we would actually see a decrease in the amount of H plus, and that would mean the pH would actually go which way? pH then would go up, yeah? So it would go up in terms of the pH because we have less H plus, which means by default you got more OH minus in the solution, right? Because they go together, H plus and OH minus. So the result of this sort of common ion effect is it will suppress that weak acid. The same thing sort of happens with a weak base as well. It will suppress it from breaking apart. And what that will do, obviously, is affect the pH. So in the case of a weak acid, we would actually expect to have a little higher pH than we would if we had just acetic acid by itself. So if we just left acetic acid in there to set up the equilibrium, break apart, we would expect a certain pH for that. By adding this common ion, it's going to force that equilibrium to the left based on Le Chatelier's principle and basically keep the acid together. And in this case, decreasing the amount of H plus, and obviously will affect our pH value. Question on that. So in most cases, the presence of a common ion usually will force things towards the side that will keep everybody together and produce actually less ions in solution. And obviously that's important here when we're talking about pH, because that is what affects the pH. So let's take a look at an example here of some of these problems here that involve common ion. There's part A and part B. So let's start with part A first. Let's just calculate the pH of a 0.2 molar acetic acid solution. The Ka value here for acetic acid, 1.8 times 10 to the minus 5. So take a few moments here and work just part A, and then we'll talk about it. Then we'll talk about part B here. Look and see how you're doing. So part A here, we want to calculate pH of a 0.2 molar acetic acid solution. Again, we are given a Ka value for acetic acid. So if you weren't sure, we should know that's a weak acid. And because this is just acetic acid by itself, this is pretty much like a problem we did in the previous chapter. This is just a weak acid problem. So we would set up an ice table using the acetic acid as our dissociation reaction. So here for A, we're going to take our acetic acid and break it apart. And this equals a Ka value 1.8 times 10 to the minus 5. In this case, we had an initial concentration of 0.2 molar. Once again, that's all we're given, so safe to assume zeros there for our starting. Our change here will be minus X, plus X, and plus X. That means when we are all said and done here, we will have 0.2 minus X, X, and X. Any questions on the ice table there? This obviously will then, like we've done before, go into our Ka expression so we could solve for X, and that would then be our Ka is our products over our reactant. So that in this case is our H plus and our acetate divided by our acetic acid. Again, going to equal 1.8 times 10 to the minus 5. Putting our numbers in there, we get X squared divided by 0.2 minus X equals 1.8 times 10 to the minus 5. And we could assume here that X is equal to 0. Once again, our K value is small, so might as well give it a shot and see what happens. We'll take our X squared divided by 0.2 equals 1.8 times 10 to the minus 5. Once again, we're going to multiply that to the other side and also take a square root of it afterwards. And that gives us 0.2 times 1.8 to the minus 5. A little square root action happening there. And that's going to give us a X value of like 0.001897. We, of course, because we made the assumption, should check it. So we check it once again by dividing it by what we were going to subtract it from and times it by 100%. And in this case, I hope we are good, and it looks like we are. We're about 0.9%, which means we are good on the check in this case. Any questions up to that point? Once again, here we're looking for the pH. So really, we just need the X value from our table. We can see that the X value equals the H plus concentration. So our H plus concentration in this case would be 0.001897 molar. That means our pH would equal minus the log of that number. And that would get us minus the log 0.001897, a pH of 2.72, which is acidic, and this is a acid, so that is good, just not basic, right? Any questions on any part of that calculation? That's pretty much the calculation we did in the previous chapter, yeah. So in this problem here, what we have going on in part A is really just a weak acid in the solution by itself or in the beaker by itself. It's going to dissociate, it's going to come to equilibrium, and it's going to give us a pH of 2.72. So in part B, what we're going to be looking at of this problem is a situation where we have really the same acid there. So we have the same weak acid. But in addition to the acetic acid being in that solution, in part B, we're also going to have some sodium acetate. So as we saw a second ago, that sodium acetate will produce those two ions that we talked about, and that will give us the sodium ion and the acetate ion. And once again, it is going to be the acetate ion here that is going to be our common ion. So we have basically the same molarity of our acetic acid, 0.2 molar, but we are adding that 0.3 molar sodium acetate to it. So let me show you sort of how the ice table changes a little bit as a result of this common ion being present. So we'll do part B here, I think. So in part B, we have the 0.2 molar acetic acid, and we have our 0.3 molar sodium acetate. So as we talked about a little bit earlier, out of those two, it is only going to be the acetic acid that's going to set up the equilibrium in solution. So something like sodium acetate, which is a salt, is a strong electrolyte. So once it goes for a swim, it's pretty much going to break apart into its ions. It's not going to stay together. So really the only thing that is going to be setting up the equilibrium is still going to be our acetic acid. So in terms of the ice table, we still want to do the same reaction, which is our acetic acid that is breaking apart into H plus and acetate. And by the way, because it is still the same weak acid, it is still the same Ka value, obviously, that we used for part A there, which is 1.8 times 10 to the minus 5. So initially here, we have our 0.2 molar. We do not have any H plus. Now for the acetate, do we have any there to start with? And the answer is yes, we do. And it's coming from this sodium acetate. So once again, this sodium acetate will break apart into a sodium ion and an acetate ion, which means what makes this ice table a little bit different than the one we just did is we will have an initial concentration there for the acetate. And by the way, once again, if the sodium acetate is 0.3 molar, it is a 1-to-1 relationship between that and acetate, which means the concentration of acetate is also 0.3 molar. So that's how we get to the 0.3 molar for the acetate. By the way, the concentration of the sodium would be what in this case? It would also be 0.3 molar, although we don't need it for the problem. It also is a 1-to-1 relationship between them. So this is really in a common ion problem. Actually, the problem for most people when they do an ice table is they zero this out. They're so used to put in a 0 here. And if you did zero this out, you're going to end up with which calculation? The one we just did. Yeah, you'll end up as basically just the weak acid again. So it's really important if you do an ice table in a common ion type problem that you do not zero that out. It's like the most common mistake that people make is to put a 0 there. The rest of the ice table really is going to be pretty much the same as normal. We are going to go minus x here, plus x, and plus x. This will then get us to an equilibrium of 0.2 minus x, x, and 0.3. The other mistake, again, it is plus x here, not minus, so it is plus x at this point. Any questions on the ice table? At this point, just like normal, we're going to go into our Ka expression, which is still the same Ka expression for acetic acid. So that's going to be our H plus and our acetate. And it's still, again, going to equal its Ka value. Putting our values in there, that gets us x times 0.3 plus x divided by 0.2 minus x equals 1.8 times 10 to the minus 5. We use the assumption on the first one. Why not use it here as well? So we're going to assume that x is equal to 0. Once again, you cannot get rid of all the x's. It is just the x's that we are adding or subtracting from somebody. So again, it's just that x and that x are the two that we would be getting rid of. And that would reduce this down to x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. Once again, here we are going to multiply the 0.2 to the other side and then divide our 0.3 to the other side. And if we do that, 0.2 times 1.8 to the minus 5 divided by 0.3 there. And that will get us 0. Sorry. It's an x is equal to 0.0000012 in this particular case. Any questions on that so far? We do want to check it like normal. So you do have two numbers there. You can use the larger number if you want, or the smaller number if one works. In most cases, both should be good. So we'll divide it by 0.3 times it by 100 just to check it. And if I didn't erase the number, that would be much better. There we go. Divided by 0.3 times 100. And once again, you're nowhere even near 0.1%. So the check is good in this case. Once again, that is going to give us our H plus concentration, as that is what it equals in our ice table. So our H plus concentration here would then be 0. Bunch of zeros there. We got there 2 4 zeros and a 2. That then can go into our pH equation of minus the log of that number there. And that would get us a pH of 4.92. Any questions on any part of that? So again, in a common ion problem, which is very commonly buffer problems, as we'll talk about shortly here, you could do an ice table, works basically the same way, but the key is you got to have that initial guy on the right-hand side. Otherwise, you're really not doing a common ion problem. So super common mistake people make. Now, what did we see in terms of the pH of acetic acid by itself versus acetic acid with the common ion? Which one was lower pH? It is the acetic acid by itself at 2.7. With the presence of the common ion, it forced the equilibrium back this way, which decreased our H plus concentration in comparison to just the acetic acid by itself. The result of that, a higher pH than we saw with acetic acid by itself. Yeah. Any questions on that there? All right, so let's talk a little bit more about maybe some other ways we could approach some of these problems here. Now, in problems where we have sort of this common ion effect because of the common ion kind of pushing back the acid, for example, or even the weak base from dissociating. What that will typically do is if you're starting with pretty good concentration values to begin with, what you start with in terms of your initial concentration and what you end up with in terms of your equilibrium concentration will be pretty much the same. And we could actually see that if we look at this, once again, if I put my X value here into here or into here, is pretty much going to be the same number, right? So if I add 0.3 and plus 0.000012, you basically still have 0.3 at the end, and you basically still have 0.2 that you started with as well. So the good news is in a lot of cases, if you come across this common ion sort of situation, there is an alternative way that you could calculate the pH without having to do an ice table, which might be a good thing. And that is basically what is referred to as the Henderson-Hasselbalch equation, which is derived from the Ka values. And the Henderson-Hasselbalch equation, or David Hasselbalch equation, which one ever you like there, is in the box here, and that is the pH is equal to the pKa value plus the log of the base over the acid. So if you have a common ion problem, which is really a buffer problem in most cases, you could use this equation in place of doing the ice table. And you can just use the initial concentrations and go in there. Couple important things. pKa value is solved by taking minus the log of the Ka value. So a pKa value, you can do minus the log of the Ka value. And this is really the version of the equation here, the two that are in the box, that you probably should use most of the time in any situation. It really doesn't matter if the solution is acidic, basic, or neutral. You can use the Henderson-Hasselbalch in all situations, as long as you always get the base on top and the acid on the bottom. Now, there is another equation that is sometimes commonly seen or used by some people, and I personally think it's kind of a waste of time in most cases, because in most cases, you're going to be asked, what is the pH of the solution? But there is a similar relationship or equation that looks at the pOH. So for example, sometimes people in a basic type of solution will use pOH is equal to the pKb plus the log of the acid over the base. So those things are switched if you use this one. The pKb value is found by taking minus the log of the Kb value. So you'll occasionally see some people use this equation, but what ends up happening after you use this equation is you still got to subtract 14 to get to the pH anyway. So you might as well just go into the Henderson-Hasselbalch equation and get the pH right off the bat, unless you're interested in the pOH. So you'll see that there is a good relationship, though, between pKa and pKb that is sometimes helpful. The pKa value plus the pKb value equals 14, kind of like the pH scale. Yeah, so the pKa value plus pKb value equals 14, which means, you know, if you happen to be given a Kb value or a pKb value and you need a pKa, you could basically subtract 14 and get your pKa value. By the way, if you take the inverse log of the pKa value, you'll get the Ka value back. So they keep going backwards as well. So you can get your Ka value from it as well. So again, those are a few different equations that are used in common ion processes, which are really buffer problems, as we'll talk about in just a second here. But again, for my money, I would roll always with the Henderson-Hasselbalch and the pH version of it. Again, works equally as good in a basic buffer situation as an acidic solution. And again, you're usually, I would say 99 times out of 100 looking for the pH anyway. So, but just in case you see it, that is a legitimate sort of equation there as well. Any questions on that there? So with that in mind, let's take a look at the one we just did, which was we had a solution of 0.2 molar acetic acid And we also had 0.3 molar sodium acetate. And we had a Ka value, obviously, for acetic acid, 1.8 times 10 to the minus 5. So first off, how do I know I should use the Henderson-Hasselbalch equation, and should I use it in every situation? The answer is no. That is a super common problem that most people do. Is like, cool, I got this equation, I'm just going to lay it up on every calculation that I have two numbers that I could throw in there. And you shouldn't do that. So really, as we'll talk about, this equation is specifically for buffers, which are common ion situations. If it is not a common ion situation or really a buffer situation, you should leave Henderson-Hasselbalch at home, yes, and not use it. So we are going to use in this situation because it is a common ion. We know that this guy and this guy are related to each other. So that gives us our common ion. And we will do our pKa plus the log of the base over the acid. Our pKa value here would be minus the log of the Ka, which is minus the log of 1.8 times 10 to the minus 5. That is a 4.74, I believe, when you do it. Now that I have the pKa value, I really have everything I need to sort of solve this. And we do want to make sure that we put things in the proper spot. So we will go pH is equal to 4.74 plus the log. Which one is the base here? That's not a trick question. Which one is the base? The Ka value goes which thing? The one that's called acetic acid. That would be the acid, which means the guy that has one less hydrogen would be the base. Yeah, so that guy should go up on top. So the sodium acetate, which is the base, should go up on top. And our acid, which is the guy that should have the extra hydrogen and the Ka value, should go on the bottom. So you want to make sure you do not flip those around. So we're going to take 0.3 divided by 0.2. Take the log of it. We're going to add it to a 474, and we're going to end up with a pH of 4.92 without the assistance of an ice table. Yeah. Question on that there. So you really do have two options in these common ion problems, which again are buffer problems. You can ice table it, and there's nothing wrong with doing the ice table. You just got to make sure you have that initial concentration. Or if you could recognize that that is the situation that you're doing, it will probably save you some time and probably a little less room for error if you just go into the Henderson-Hasselbalch equation and solve it for the pH. But you absolutely could do it either way. It's really your sort of opinion as to how you feel you want to do it. Any questions on that? There. So once again, I can't emphasize enough, don't go crazy with the Henderson-Hasselbalch equation and use it on every calculation. It is specific for this type of situation that is going on. All right, so why don't we try one here? What is the pH of a solution that contains 0.3 molar, we can go with formic acid, and 0.52 molar potassium formate? All right, let's take a look and see. So in this case, first thing you should look at is perhaps are these things related to each other, and hopefully you can recognize that this guy here, which is formic acid, is related to this potassium formate, as that is basically formate and potassium together. That's kind of like a weak acid and its conjugate base is basically what we have there. They are related to each other. The only difference is 1H plus. And again, that potassium formate will break apart into a potassium ion and a formate ion there. Okay, actually, one arrow heading in that direction. So that guy will completely break apart into those two ions, and that's going to create our common ion in this case. And again, you should hopefully see that it's related. If I can get this thing to right, there we go. All right, there we go. So also sometimes people have a hard time remembering or figuring out which one is the acid, which one's the base here. So once again, the acid, because it's got to donate the H plus, will have the extra hydrogen. And usually the base will have some type of spectator ion hanging out there, like a potassium, a sodium, lithium, something like that. So that's usually a good way to you're able to recognize which one's which in case you're not sure. Because we do see that they are related to each other, we do have the common ion here. We can go directly into the Henderson-Hasselbalch equation, which once again is our pH equals our pKa plus the log of the base over the acid. Our pKa value here will be our minus the log of the Ka, so we'll do that there. Gets us minus the log of 1.7 times 10 to the minus 4. That's going to get us, looks like a 377. And that would get us 3.77 plus the log of the base. So once again, we want to make sure we do identify that correctly, which would be that guy right there at 0.52 divided by our acid there at 0.3. Once again, we do want to divide those numbers first and then take the log of it. So that is 0.52 divided by 0.3, and then we're going to log it. And then we're going to add it to 3.77. And that's going to give us like a 4.01 in terms of our pH in this case. Yeah. Any questions on that? Now, if you did choose not to use the Henderson-Hasselbalch equation or was not sure if you should, you again could do an ice table, and it would be the acid, the weak acid, the only thing that would be setting up the equilibrium. So you would have something that looks like this. And once again here, we would do our initial of 0.30. We would have our 0. And as we were talking about earlier, very important that we should also have an initial right there. And that would be where our 0.52 would go. Once again, if you did not put that initial there in that ice table, you're not doing the common ion problem that we're looking at. You're just doing the weak acid problem. That would be minus X plus X plus X. And again, that would go into our Ka expression, which would give you X 0.52 plus X divided by 0.30 minus X equals our 1.7 times 10 to the minus 4. Once again, here you would solve for X. X would equal the H plus concentration and then into the pH, which should give you the same number. So again, it is just your personal preference as to which way you want to go. You can see that probably the top part might be a little bit quicker. And again, maybe a little less room for error, like I said, by doing the bottom, but the bottom should work just the same. Any questions on either of those there? Okay, so really what we're talking about here, again, is these common ions, and really what common ions are more commonly referred to are buffers, and buffers are really solutions that are made up of common ions in there. It has either a weak acid in its conjugate base or a weak base in its conjugate acid. And those are really what buffers are. And buffers are really the place where the Henderson-Hasselbalch equation should really only be used when you're doing it. So let's talk officially about what buffers are and sort of how they work. So a couple of really important things about buffers is a buffer is really a combination of really one of two combinations. You could have a weak acid and its conjugate base, and it's sometimes referred to as the salt of its conjugate base. And it's referred to as the salt of its conjugate base because, frankly, it's got like a sodium ion, a potassium ion, something there that's just going to balance out the charge. Or you could have a buffer that's made up of a weak base and its conjugate acid, which again is also sometimes referred to as the salt of its conjugate acid. First off, those two things are the same definition we talked about in the last chapter, which is our Bronsted-Lowry definition. The only difference between those two things should be 1H plus. And that's one way you can recognize should these things maybe be a buffer. So if you're looking to see, will these things make a buffer, or can these things be a buffer? You got to have that relationship of basically a weak acid and conjugate base, which is really just one H plus relationship, or a weak base and its conjugate acid, which is also one H plus relationship. But it does have to be a weak acid or a weak base. You cannot have a buffer made up of a strong acid or a strong base. And we'll talk about why you cannot have a buffer that is made up of a strong acid or a strong base. And it's really because of both of these things are actually in the solution to begin with. So when you make a buffer, you have in that little beaker or whatever you made your buffer in, it has both the weak acid floating around and the conjugate base part of it floating around. And having both the acid part of the buffer and the base part of the buffer in the solution is essential to how it's able to actually work. And it's all same thing if you actually made it out of a weak base and its conjugate salt. Now, if I try to make a buffer out of a strong acid or a strong base, the problem with that is a strong acid and a strong base, they will do what? Will they stay together or completely break apart? Strong acid or strong base will completely break apart. So for example, if I wanted to make a buffer out of HCl, it is 100% going to break apart into H plus and Cl minus. Now, if we're talking about acid and base for a buffer, this is our acid, right? This would be our conjugate base. And frankly, in solution, none of this would exist. All you would have is a base, which means, as we'll talk about shortly here, it has no way to function as a proper buffer. So that is why you can never have a buffer that's made up of a strong acid or strong base, because you can only keep in solution one part that you need, and you need them both in there. The reason we could do it with, again, a weak acid or a weak base is when we put that in solution, for example, like our acetic acid, which is a common buffer, it will set up that equilibrium, and we will have H plus and acetate floating around in that solution to begin with. So in a solution made up of acetic acid and sodium acetate, we have the acid part in the solution and we have the base part in the solution to begin with, and they will remain in there because it's going to set up that equilibrium. And when you make the buffer, you're going to help it along by usually adding more sodium acetate, which is going to allow a little bit more of the base part to be in there from the sodium acetate, because that's the common ion effect there. It will also push back to make sure you have a good amount of the acid with the presence of that common ion. So when you make a buffer, one way to make a buffer is simply just take both things and pour them together, basically, and you'll make the buffer. And by doing so, you'll have a good amount of both of those guys in a solution to begin with. Once again, you'll have your base part in there of the buffer, and you will have your acid part in the buffer. And again, that cannot happen with anything that is strong acid or strong base. So what does really a buffer do? There's a misconception about what a buffer is. Most people will say, well, a buffer is a neutral solution, and that is not necessarily correct. A buffer is a solution that will resist changes in pH, even when you add additional acid or base to it. What that means is, for example, you could actually make a buffer at any pH you like, from 0 to 14. You can make a buffer at any of those pHs. So for example, if you made a buffer at a pH of 4 and you added acid to it, the pH would not jump way low. So it will basically stay around 4. Will it go down a little bit? It will, but it won't go from like a pH of 4 all the way down to like a pH of 1. So you won't see a really big jump in the pH. Same thing if you made that buffer at 4 and you added some strong base to it, it will stay around 4. Will it go up a little bit? It probably will, but it will not go from like a pH of 4 to like a pH of 12. So a buffer is able to resist really big changes in pH when you add additional, say, strong acid or strong base to it, as long as your buffer is made correctly and the acid and base you're adding is correct as well. And it will not really see big jumps in the pH. So although you can definitely have a buffer that's neutral, you can just as easily have a buffer that is basic and a buffer that is acidic as well. Any questions on that there? So let's talk about really how a buffer works here. Let's see, I got a page maybe I can write on. Yeah, perfect. So let's first talk about what happens when we add a strong acid or strong base to a non-buffer situation. So we'll use everybody's favorite example, which is water. Water, by the way, is not a buffer. So if we take water and we decide to add some hydrochloric acid to water, it will, as we know, 100% break apart into H plus and Cl minus. Right? So basically 100% of it will break apart there. What I just did, right, is I have my water at its water pH, we'll say ideal conditions of 7-ish, I guess. But by putting the HCl into that water, basically, we just added a bunch of H plus ions that are floating around in there, some chloride as well. So we just added a ton of H plus to that water solution, which means the concentration of H plus just went way up, which means we would expect to see the pH go way down. So for example, maybe we did have water at a pH of 5 or 6 or 7, you pick it, and we add some HCl to it, and we will see the water's pH maybe drop to a pH of 1, a really big jump in pH because we just introduced to that solution a lot of H plus really, really quickly. By the way, you take the pH of water that's been sitting out a while, is it 7? It's actually slightly acidic in most cases because it picks up some CO2 from the air, makes carbonic acid, increases the H plus concentration, lowers the pH. People are sometimes surprised. It goes, my pH meter broken? This water is not 7. Yeah. So depending on how good your filters are and stuff like that and how long it's been sitting out, you know, water will be somewhere in that 5-ish, 6-ish range, maybe. A lot of times 5-ish range because of that. So what we see here when we do add a strong acid to water, which is not a buffer, it basically just creates a ton of free H plus, and that is obviously from our pH equation very much what affects it, since it's pretty much all about the H plus concentration. So what happens if we take a strong base and we add it to water? So if we took something like sodium hydroxide and we added it to water, the same effect's going to sort of happen here. We're going to get it completely dissociating into sodium ions and hydroxide ions. And we will 100% get these guys to basically dissociate. Now, this is a little different. In this case, though, we just jumped into our solution of water, a bunch of hydroxide, and also some sodium ions floating around in there. And because we put a bunch of hydroxide ions, that concentration is going to go up. And because hydroxide and H plus are tied to each other, as the hydroxide goes up, the H plus concentration should go down, right? So we'll see a big jump in the H plus concentration. As one goes up, the other goes down. And a result of that is we will see the pH actually go up. Because of that, more hydroxide in the solution, less H plus in the solution, we will see a really big jump in pH with water because it's not a buffer, because we basically just increase the OH minus concentration. So maybe it goes from a pH of 5 up to like a pH of 9 or something like that, based on how much base you throw in there, how much squirts you do in there and stuff like that. So in a non-buffer situation, what ends up happening is there is a lot of H plus formed really quickly. There's a lot of OH minus formed really quickly, which is why these things are considered strong acids and strong bases, right? They pretty much just need to go for a swim and they're going to produce H plus or OH minus, which will have a pretty good effect on the pH, right? So let's talk about what would happen if we take these two same things, but we actually add it to a buffer solution instead. So we'll use a buffer solution. I'm just going to use a different one because everybody uses acetic acid. Let's use hydrofluoric acid and a little sodium fluoride. Yeah. I feel like writing acetic acid right now. So hydrofluoric acid is a weak acid. Sodium fluoride is the salt of its conjugate base. Out of the sodium fluoride part, the real part that's the buffer part is which part of it? The really active part is the F minus part, right? That is the conjugate base to HF. The sodium ion that's in there just floating around having a good time, not really doing much, going for a free swim. Can't blame it. It's free. It's hot outside, going for a swim. But it's really the F minus part of that. That is why, again, it's referred to as a salt of its conjugate base because it has a sodium to balance out the charge. It's really a spectator ion not doing much. So what we have here in solution before we begin is by adding both of those things, we are going to get the HF to really set up that equilibrium. And we will have some H plus and really F minus present in the solution to begin with. So in our buffer solution to begin with, we really have an acid part and we have a base part of the buffer, which is essential to how a buffer really works. So again, this is, if you want to think about it, the acid part of the buffer, and this is obviously the base part of the buffer. So now when you come along and decide, I'm going to toss my HCl into here. When I toss my HCl into my buffer solution, it is going to react with what part of the buffer? Will it react with the acid part or the base part? They are called acid, what type of reaction? Acid base reactions, right? That's what they're called. You never hear acid-acid reaction or base-base reaction. It sounds funny, yeah. So when you add an acid, it's going to react with the base part of the buffer. So when you introduce HCl to this buffer solution, it is actually going to be the base part in this case that's going to react with it. So the sodium fluoride in this case will react. You're basically going to get a double displacement reaction, positive, negative, positive, negative. These two guys are going to swap partners. And what we're going to get on the other side here is the formation of HF and a little sodium chloride, I think. There we go. In this case. First off, any question on that reaction? So let's analyze what we just made here. We just made some more HF, right? So HF was part of the buffer solution to begin with, which means it's not going to affect the pH. And by the way, that is always what happens in a buffer reaction. You react one part of the buffer, but you always make the other part. So you kind of use up some of the buffer, but then make the other part of the buffer. And that is always what happens. In this case, we also made a good salt right here, sodium chloride, which we are familiar with. And you're going to tell me sodium chloride is an acid, base, or neutral salt. It is which one? Sodium chloride is a neutral salt, right? It is sodium, right, which is group 1, which is neutral. It is Cl minus, which comes from HCl, which means it's weak. This is a neutral salt, right? So that clearly is not going to screw up the pH. The HF that was in the buffer solution to begin with is not going to screw up the pH. So really, it is actually what we do not see here that we did see in the water case as to why the pH doesn't get all messed up. What are we not seeing here that we did see here when we added the acid to the water? That would be important for pH. Yeah, when we added the HCl to water, we produced a ton of hydrogen ions, right? Which affected the pH. When we added it to our buffer, we did not produce any more hydrogen ions. So no hydrogen ions produced. Which means if there is no new hydrogen ions produced, the concentration of H plus will stay relatively constant. And if the H plus concentration stays relatively constant, the pH then should also stay relatively constant. And that is really how a buffer is able to function, because it has the base part in this example. It's able to tie up the H plus, so it is not freely floating around in the solution to affect the pH. And because you didn't produce any more free H plus, you will be able to maintain your pH. Now, I did say relatively constant, and what I mean by that is if you put a pH meter in there and you add some HCl to a buffer, you will see the pH go down. But it will not jump giantly like we were talking about from like a 5 to a 1. Maybe it starts at pH of 5 and goes to like 4.96 or something like that, or 4.9. It's a very small gradual decrease, but it will not have a giant jump in the pH, because frankly, you are producing a little bit of HF, and that will produce a little bit more H plus, but you will not produce a ton of H plus like you do when you add a strong acid to it. Any questions on that there? So let's take a look at what would happen if we added the sodium hydroxide to the same buffer. So we'll use the same example here. We'll use our same hydrofluoric acid and sodium fluoride buffer. And in this case, we're going to add some sodium hydroxide to it. So we have our same sort of situation here where we have our HF that's set up. It's a little equilibrium there. We got some H plus and a little F minus going on. We once again have our acid part of the buffer there. We have our base part of the buffer. So now when I go and add my sodium hydroxide to this buffer, which part of the buffer is it going to react with, the HF or the sodium fluoride? The sodium hydroxide is a base, which means it should react with which one? It is a 50-50 shot. It is going to be the acid part, right? Once again, acid-base reaction, right? So it is going to react with the acid, which is the HF. This is going to do an acid-base reaction, right? Which means you should create a salt and water. Also a double displacement reaction, in case you're not sure. The sodium will come over here and the hydrogen will come over there to make the water. That will produce us some water and a little, sodium fluoride. There we go. So when we add our sodium hydroxide into our buffer here, this is the reaction that we're going to get. And we do see a couple of things formed here. We do see that we made water, which definitely should not screw up the pH. Once again, like the other, we make sodium fluoride, which was part of the buffer to begin with. And again, that always happens. You always make the other part of the buffer when you're reacting it. It is once again what we do not see here that we do see on the previous page when we added the sodium hydroxide to water. What did we see when we added sodium hydroxide to water? We saw a bunch of hydroxide ions, right? So we saw a bunch of these hydroxide ions that were added. We do not see hydroxide here on the product side. So in this case, no new hydroxide ions were produced. Do you have a question? Yeah. And because no new hydroxide ions were produced, the OH minus concentration will stay relatively constant. That's important because once again, hydroxide and H plus are tied to each other, which means if the hydroxide concentration stays constant, the H plus concentration has to stay constant as well. So that means that the H plus concentration by default will also remain relatively constant. And because both of those stay relatively constant, we will see that the pH will also remain relatively constant. So again here, because we have the acid part of the buffer in this case, it's able to tie up any new hydroxide from entering the solution as in the form of water. It basically ties it up as. And the result of that is it keeps the hydroxide concentration constant, keeps the H plus concentration constant, and thus the pH does not jump around really big. So again, we're talking about not a really large jump in the pH. If you were monitoring it with a pH meter, again, if you added some base to your buffer, you would see it go up. And again, if you had like a pH of 5, maybe it goes up to 5.1 or 5.06, something like that. But it will not go from like a 5 to a 12 pH or anything like that, as long as you have everything correct in terms of your buffer concentration and your acid and base concentration. Question on how a buffer works. So essentially, when you make a buffer, a lot of times what people try to do is they try to make a buffer where you have pretty much good amounts of the acid part and the base part. And if this is your buffer. And what happens is as you add acid to your buffer, it will react with the base part of the buffer, but it will make more of the acid part of the buffer. So what happens is the acid part of the buffer goes bigger. And the base part of the buffer gets a little bit smaller as you use some up. Same thing happens the other way. If you add some base, it will react with the acid part of the buffer, but it will make more of the base part of the buffer. So it's kind of like regenerating half of the buffer every time you do a reaction. So you'll have some base part regenerated of the buffer. You'll have your acid part here of your buffer. That's your buffer as well. There is a limit to a buffer's capacity. It's sometimes called buffer capacity. What would happen if I didn't read the instructions, which would never happen, I'm sure. And maybe the instructions say, hey, grab off the bottle that's the 0.1 molar hydrochloric acid, but you grabbed like the 18 molar hydrochloric acid and decided to add it to your buffer. What would happen to your buffer? Yeah, something like that, or if you just continue to add a bunch of acid nonstop or really high concentration of acid, all that H plus that you would be adding from the acid would start to eat up the base part of the buffer, right? And at some point, you're not going to have any more of the base part of the buffer there to react with additional H plus that comes in. So at some point, you blew through your buffer, basically. And what's going to happen if you continue to add the H plus is you're now going to saturate the solution with a bunch of H plus, which at that point, you would expect the pH to do what? Jump pretty big, yeah, because you just added a ton of H plus, you blew through the buffer, basically. So there is a limit to the buffer. It's sometimes referred to as buffer capacity. It's important, the concentration of your buffer and also the concentration of the acid or base that you may be adding to your buffer. Same thing could happen on the base part. If you added way too much base or too strong a base, you could just blow right through the acid part of the buffer. And at that point, you would just be dumping in there a bunch of hydroxide ions, and you would see a pretty big jump in pH at that point. So when you do make a buffer, a lot of times you want to think about what concentration of the buffer do you want to make to keep enough of the acid and base in the solution that will handle whatever it is you're going to be kind of tossing in there, so you don't kind of blow through it. First off, any questions ultimately on how a buffer works? The last thing we're talking about here for a moment is how we can use the Henderson-Hasselbalch equation, which is really the equation that we use for buffers, because buffers, frankly, are common ion problems. They have a weak acid and conjugate base, which are two ions that are related to each other, and they have a weak base and a conjugate acid, which again is a common ion situation. Now, if you wanted to make a buffer, or how do you know, what you should choose to make a buffer in? You could use the Henderson-Hasselbalch equation here to help you decide what might be a good choice to make a buffer at. So let's say, for example, I decided to make the concentration of the base part of the buffer pretty much equal to the acid part of the buffer. So I decided to make those concentrations the same. That means when I go into my Henderson-Hasselbalch equation, the pH would equal the pKa plus the log of, if this number on top and this number on the bottom are the same, what number do you get? Log of 1? Yes. Log of 1 equals 0. Yeah. Which means usually to select a good choice to make your buffer out of, you're looking for a weak acid or conjugate or weak base that has a pKa value of plus or minus 1 of your desired pH. So usually plus or minus 1 of your pKa value is what you're looking for of your pH. So for example, if I wanted to make a buffer at a pH of say 9-ish, I want to make that buffer. And I looked at acetic acid, which we saw earlier in the problem, where the pKa value was 4.74. Would that be a good choice to make my buffer out of? That and sodium acetate? It would not. You could do it, but you're going to be adding a lot of junk there to get it to work, and it's not going to work really well. I might want to choose something like NH4 plus, which has a pKa value of like 9.25. That's a much better choice to make that buffer out of. And that means that you can really look at a weak acid table or a weak base table, convert either the Ka value or Kb value into the pKa or pKb value. And what you want to choose is the one that's closest to whatever your desired pH is. Not all choices are always the best choice. That is really what you would want to look for. It's something where you have a plus or minus 1 of the pKa value to your desired pH is what you're looking for to make your buffer out of. Any questions on that there? Okay, we're going to lay it up there for